So this is the third video for chemical bonding in the A-level syllabus. In the second video, we have looked at how to draw the dot and cross diagram for covalent compounds and polyatomic ions. So from there, we can determine the structure or the Lewis structure of a molecule. And in this video, we're going to look at how we can therefore determine the shape of a molecule. Alright, in the O-level syllabus, if you can recall, your teachers have been teaching you that carbon dioxide has this particular linear arrangement, whereas water has this particular arrangement which looks like Mickey Mouse. So in this video, we're going to learn why is it that the molecules have such a shape. So the theory that governs it all is known as the VSEPR theory, or valence shell electron pair repulsion theory. So there are three very important points to remember. The first of which is that electrons or electron pairs, they tend to arrange themselves as far apart as possible to minimize repulsion. Now electrons or electron pairs, they are negatively charged. So like charges, they tend to repel, and for maximum stability, they will try to arrange themselves as far apart as possible. So an example would be, let's say, carbon dioxide. In carbon dioxide molecule, where do we find the electrons? We find them in the covalent bonds. Okay, so these covalent bonds are filled with electrons, and electrons, they tend to repel one another. All right, so the best arrangement that we can have where the electrons are the furthest apart from each other would be when they are 180 degrees apart. So that is why carbon dioxide have this particular arrangement, so that the bond pairs, the electron pairs, are as far apart as they can be. The second point is that multiple bonds are treated as a single bond pairs. So over here, carbon dioxide has a double covalent bond. So in VSEPR, we just treat them as one bond pair. Okay, in VSEPR, there's also something called a lone pair. What is a lone pair? We find them in molecules like ammonia. Okay, if you look at ammonia, if you draw the Lewis structure, you find that there is a pair of non-bonding electrons on nitrogen atom. We call this a lone pair, okay, because it is not involved in bonding. The electrons that are found in covalent bonds, we call them bond pairs. So the last point to remember is this, that lone pair repulsion, the repulsion between two lone pairs is more severe, is stronger than the repulsion between a lone pair and a bond pair, and the least of the repulsions will be between a bond pair and a bond pair. So with these 3 points in mind, let us see how it affects, or how do we use it to determine the shape of a molecule. Now these are the 4 steps to find the shape of a molecule, as well as the bond angles between the bonds in the molecule. So what are the 4 steps? First, you need to determine the number of electron pairs. Okay, by electron pairs, I mean bond pairs plus lone pairs. So for example, if we look at ammonia again, there are actually 4 electron pairs made up of 3 bond pairs and 1 lone pair. Now from the number of electron pairs, we can actually find the parent shape. Now what do I mean by parent shape? Now if I have 4 electron pairs, okay, how do I separate the 4 pairs of electrons as far apart as possible? Okay, the answer is this, that you have to put them in what we call a tetrahedral arrangement. Okay, if we put the 4 electron pairs in a tetrahedral arrangement, that is the furthest they can be apart from one another, which gives rise to an angle of 109.5 degrees. So that's the furthest in which the 4 electron pairs connected to a central atom can be separated. So this is called the parent shape. The parent shape is tetrahedral. Okay, after that, in order to find the shape of the molecule at hand, you then erase the lone pair. So if there's a lone pair, you want to erase the lone pair. and then you name the resultant shape. So for example, if you look at ammonia again, the lone pair is here. So I'm going to erase the lone pair. And if you look at the remaining shape, how would you name something like this? It's actually, it looks like a pyramid with 3 faces. So how do we name it? We call it trigonal pyramidal. Okay, so there are teachers who would teach that you simply have to memorize how many bond pairs plus how many lone pairs equals to what shape. But personally, I think that you don't really have to memorize. Once you follow this rule, the shape, the resulting shape would actually tell you, would actually hint to you the name of the shape of that molecule. Next, to find the bond angle, you need to check the number of lone pairs. If there's a lone pair on the central atom, remember lone pair bond pair repulsion is going to be greater. So what happens is that the lone pair is going to push the bond pairs closer together. Alright, so if the lone pair were not to be there, the bond angles between your HN and H again is ideally 109.5. This is the angle of a tetrahedral shape. However, because there's one lone pair, the lone pair is going to exert a greater repulsion on the bond pairs, causing the bond pairs to come closer together. So in ammonia, the angle between HN and H is likely to be around 107 degrees. So now what I'll do is that I'll go through all the different shapes that we can get for all the different combinations of bond pairs and lone pairs, starting from the parent shape. Now if we have 2 electron pairs, the arrangement where we can put the electrons the furthest apart would be like that. So if we have 2 bond pairs, then it would have a linear shape because it's a straight line. Alright, for 3 electron pairs, the furthest that we can separate them would look something like this, where the angle is 120 degrees apart. We call this trigonal planar. So if a molecule were to have 3 bond pairs, then we would call it trigonal planar. However, if we convert one of the bond pair to a lone pair, that means we have 2 bond pairs and 1 lone pair. Now what will the resulting shape look like? Let's see what happens if we erase one of the bond pair. It looks not straight. Alright, so what do we call it? We call it bent, or we call it V-shaped. Okay, for 4 electron pairs, the furthest that we can separate them would look something like this. This is called tetrahedral. Okay, so the 4 electron pairs around a central atom would be 109.5 degrees apart. So if a molecule were to have 4 bond pairs, then we call it tetrahedral. And what happens once again if we convert one of the bond pair into a lone pair, meaning we have 3 bond pairs and 1 lone pair, then it's going to look something like this. I'm going to erase. So the resulting structure, if you can see, looks like a pyramid, a trigonal pyramid. So we call it trigonal pyramidal. Okay, if we go on further, erasing one more bond pair, so we convert one more bond pair to a lone pair. So we have 2 bond and 2 lone. Now what is it going to look like? So I'm going to erase one more bond pair. If you take a look at the resulting shape, it's obviously just bent or V-shaped. Now if we have 5 electron pairs around a central atom, the furthest that we can separate them would look like this. So the electron pairs around the central atom will be as far apart as they can be. Now what do we call this shape? We call this trigonal bipyramidal. So why is it called trigonal bipyramidal? Is because it looks like there are 2 pyramids one on top, so this is one pyramid, and then there's a pyramid that's below, so we call it trigonal bipyramidal. So a molecule with 5 bond pairs, we call the shape trigonal bipyramidal. Now what happens if we were to convert one of the bond pair to a lone pair? Now the shape is going to look something like this. It's not immediately obvious, but if you were to rotate your head 90 degrees to the right, I hope you can see that it looks like a seesaw. Alright, so we call this shape a seesaw shape. And what happens if we go on further to convert one more bond pair to a lone pair? We're going to end up with a shape looking like this. So meaning we have 3 bond pairs and 2 lone pairs. So it's going to look something like this. We're going to erase 2 bond pairs, and if you take a look at the resulting shape, it actually looks like a T, or the letter T, so we call it T-shaped. When you have 6 electron pairs around a central atom, what is the furthest that we can separate them? It will look something like this. Okay, what do we call this? We call this an octahedral shape. So meaning if you have a molecule with 6 bond pairs, then we call it octahedral. Now what happens when you convert one of the bond pairs into a lone pair, meaning you have 5 bond pairs and 1 lone pair? So the shape will look something like this. I'm going to erase a bond pair. So what do you call this? Again, I hope you can see that it looks like a pyramid, but this pyramid has a square as the base. So what do we name it? We call it square pyramidal. And lastly, if I were to erase one more bond pair, so we have a configuration of this. Okay, let me redraw it. If I were to erase one more bond pair, so I've erased one and I erased the other one, what I have here, so 4 bond pairs and 1 lone pair. Now what would you describe the remaining shape? Now this is called a square planar. Alright, why is it square planar? Because here there's a square, and then they all fall on the same plane, so square planar. So what I've shown here are the names given to the shapes corresponding to the different combinations of bond pairs and lone pairs. So once again, it is summarized over here. Some of y'all may find it easier to memorize, but once you understand how the names are being derived, it makes it so much easier to memorize. So right now what we'll do is that we'll apply VSEPR to the different molecules to obtain the shape of the molecule as well as the bond angles between the bonds. So the first example would be nitrogen dioxide. We have seen earlier that the structure of nitrogen dioxide looks like this. So that is where students get a dilemma as well, because how many electron pairs are there? Do we consider that lone electron to be an electron pair? So the answer is actually yes. Okay, so over here there are essentially 3 electron pairs, so the parent shape of nitrogen dioxide would be trigonal planar. However, the fact that this lone electron is not an electron pair, there's only 1 electron instead of 2, you would expect that the repulsion will not be as great. Okay, so what is the shape of nitrogen dioxide? It will be bent, and the bond angle of nitrogen dioxide between your O-N-O bond is likely to be more than 120 degrees. Our reason being this is just 1 electron instead of a pair of electrons. Next we look at water. Water, we have learned to draw the dot and cross diagram since O levels. So water looks like this. You have 4 electron pairs surrounding the central atom. So 4 electron pairs, remember the shape is tetrahedral. But for water, you have 2 lone pairs. So if I were to erase the 2 bond pairs, what I have remaining again is V shape or bent. So that is why in secondary school your teachers used to teach you to draw water in a V shape or a bent shape. That's because according to VSEPR, the shape of water is indeed bent. How about the angles? In a conventional tetrahedral, the angle is 109.5, but if you can recall the rule, for every lone pair present on the central atom, you would subtract 2 of the bond angle. So the bond angle in water, your HOH bond angle is roughly around 105 degrees. Next, we look at carbon dioxide. Carbon dioxide again is a molecule that we have drawn since O levels. There are 2 double bonds from the central carbon atom to the oxygen atoms. So in VSEPR, we treat multiple bonds as a single bond pair. So there are 2 bond pairs, there are 2 electron pairs and 2 bond pairs around carbon. So the shape is very straightforward, it's linear, and the bond angle is 120 degrees. For ammonia, ammonia has this particular Lewis structure. So if we look at it, there are 4 electron pairs. The parent shape will be tetrahedral. Tetrahedral looks like this. So however, one of the electron pair on nitrogen is actually a lone pair. So I'm going to erase the bond over here, and the resulting structure, I hope you can see, represents that of trigonal pyramidal. Okay, for in a conventional tetrahedral arrangement, the angle is 109.5 degrees. So that is one lone pair on nitrogen, which means that the bond angle, your HNH bond angle, is going to be slightly less than 109.5, so it's around 107 degrees. Next, we look at phosphorus pentafluoride. Now this is something new, so let's try to draw the dot and cross diagram. Phosphorus is surrounded by 5 fluorines. This is step number 1 in drawing your dot and cross diagram. Step number 2 is to find the number of bonds, or rather step number 3, because this is not a polyatomic ion. Step number 3 is to find the number of bonds each surrounding atom can form. Fluorines have 7 valence electrons, so all of them can form only 1 bond. Step number 4, form the bonds to the central atom. Step number 5 is to find any remaining electrons. For the determining the shape, we are only interested in the central atom. So phosphorus have already used up all 5 electrons. There are no remaining electrons. So this is the Lewis structure of phosphorus pentafluoride. There are 5 electron pairs around the central atom. All of them are bond pairs. So we call this trigonal bipyramidal. Okay, for trigonal bipyramidal, there are 2 types of bond angles. Okay, why is that so? It's because we have 2 different types of fluorines. Okay, we have those that are found at the apexes, at the top and bottom of the pyramids. We call this the axial fluorine atoms. We have those in the middle that forms the trigonal plane. We call this the equatorial fluorine atoms. Okay, so between the equatorial atoms, fluorine atoms, we have an angle of 120 degrees. Between an axial and an equatorial fluorine atom, we have an angle of 90 degrees. So for those of you who were earlier wondering why do I choose certain PF bonds to erase when we are converting bond pairs to lone pairs, there is a theory behind it. We want to minimize what we call 90 degrees repulsions, but I shall not go into that in this video. The last molecule is chlorine trifluoride. Now this is a very unique molecule. Let's try to draw the dot and cross first. We have one chlorine surrounded by 3 fluorines. Step number 2 doesn't apply because it is a neutral molecule. Step number 3, we need to determine the number of bonds that each surrounding atom can form. So the answer is 1 because it has 7 valence electrons. Step number 4 is to draw in the bonds. Step number 5 is to write in the remaining electrons. And once again, we will just focus on the central atom, which is chlorine. So chlorine has already shared 3 electrons. It has 7 valence electrons, means that it has 2 more pairs of electrons. So if we look at chlorine trifluoride, there are actually 5 electron pairs. 5 electron pairs, the parent shape is your trigonal bipyramidal. Out of these 5 electron pairs, 2 of them are lone pairs. So what do you call the resulting shape? We need to erase 2 lone pairs. So there, the resulting shape is your T shape. So now, chlorine trifluoride actually has T shape, and the angles between your fluorine-chlorine-fluorine bond will be 90 degrees.